Okay, this is lecture 39 by Harvey Friedman on a subject called embedded maximality, which was tangible incompleteness some time ago. Anyway, please.
Thank you. Okay, it's taking me a while, but I'm getting this polished up. I think things are very stable. There's some simplifications and improvements since last time, um, and so there's definitely going to I have to give another talk on this, of course. I There's a good chance. I think I should finish next time on this chapter, uh, as long as I get going on this seriously. All right. So the table of contents is changed only. This is all the same. Just changed a little bit when we get into the real thing. The real thing is section 3.6, beyond finite usability. The finite thing being long since worked out completely. And I think this table of contents is the same, but the content is a little bit better. Uh, and then I go ahead and prove. So OEU, if you remember, means order and extension usability. And this means one dimension and any number of and any size. I think I should. This is silly here. That's what I meant. Yeah, one dimension and any size. Uh, this is two dimensions in any size. This uses nothing. This is provable. Uh, Let me think. I think that's EF. That's right. There's nothing. It's just EFA. I think it's just you can say it's EFA or RCA not, of course. Yeah, let's just leave that alone because there's nothing serious in this. It's easy. This uses omega 1 and it has the 5 sections. It's a little bit, the notation is a little bit uh, a little bit changed in the way I set it up a little different. Um, then we have the situation where the size of the function is 2. The size of the field is 2. This is the size of the field is 2 in any dimension. You can also get away with omega 1. So when you put 2's either place, you can get away with omega 1. So this is nice because in theory, at least, a mathematician can stay in very weak fragment of ZF uh, and follow this proof without any large cardinals. Then the large cardinals come in here where um, we do any dimension and any size of the finite part of the finite function of the field, and we fix K. So we just use K minus 2 subtle cardinal. And after some preliminaries about the subtle cardinal hierarchy we need, we proceed very similarly to what we did with omega 1, except there's large cardinal combinatorics stuck in here. Everything else is the same. Yeah, I'm going to reorganize this so the common parts between these things are done once or mostly done once rather than repeated. So I have some organizational work to do. Okay. And then, by the way, there's always a dichotomy between whether the function goes all the way to the right endpoint 1, in other words, the field contains 1, and it doesn't. Because when the field doesn't contain 1, there's an interval containing 1, which is not part of the function at all. And that changes the details a little bit. And there isn't a good way for me to avoid duplication of that. So I just do it. I just do it first, assuming that that number one is in the field. See here, actually, I'm using n. This is not. We'll keep the notation the same. N, except that it's n minus one. Yeah. So this is kind of screwed up. Yeah. So I have to use n minus one because the number of these things is going to be n. The number of these numbers is n. Yeah. Let's see if I did this, screw this up here. Um, this is not right. Yeah. This is just proper bookkeeping here. So you want these there to be n numbers here. Here's where it stops. And the rest of this stuff is blank, so to speak. And this corresponds to what's in the field. Here's where the field is just 0 and 1, and then here's where the field is 0 and 1/2. Okay, let's see if I wrote the other ones right. So that's now right. And that's right. And this is wrong. All right. Okay, so this is the case. This is the case where you use large cardinals, where you have any dimension and any size of the given finite part. In one case, we fix in the first case, we fix the size of the finite part and let the dimension vary. And we get k minus 2 subtle cardinal we need. And here we need n minus 2 subtle cardinal. If you fix the dimension and allow arbitrary, well, at least 3 finite part. And this takes care of the whole situation. Now I haven't started to polish this up. So this probably will look a little, yeah, this might be a little different, the way this is going to be exposited. But this is the stuff which was done before in some other related context, where you look at the weak order extension usability. And I don't remember whether last time I had done this right. I now have a very good form of WOEU. We'll be going over that. And here's where you stay in ZFC, but you iterate the exponential function on omega. So it's these Beth numbers. And this is Erdős-Radó combinatorics is what's used here. Here we use the subtle cardinal hierarchy combinatorics. And here we use the Erdős-Radó combinatorics. Yes. And that's not new, that's been done before, but I have to polish it up and make everything integrated. So let's just look. There'll actually be 2 sections here, one with k fixed and one with n fixed, just like I had here. So there are going to be 6 of these sections. In other words, 6 of these big sections. Well, maybe 7 with this one. This one's a special. Actually, I should do also 1n is trivial. for every K, OEAK, OEU K comma 1 is also trivial. Yeah. So I probably should say both of these at once. So that'll be a little tiny change, but that's trivial stuff. And then, so we basically have four of these. Two of these fixing two. See 3, 8, and 3, 9. 3, 8, and 3, 9. Two of these fixing the number 2, which is either fixing the dimension 2 or fixing the finite part to be 2. In which case you can do it in ZFC. In fact, you can do it using omega 1. In particular, you can do it in Z3 and fragments of Z3. All right, now then I go to the full-blown thing, which is any dimension and any finite size. And here, if you fix n, if you fix the dimension, you need the dimension minus 2 subtle cardinal for k greater than equal to 3. And then if you fix the finite, the size of the field of the finite part, you need n minus 2 subtle. When I say you need, my proof needs. Now, I didn't do any reversals here, except that I did reverse. Yeah. I did reverse the statement, the full-blown statement for all k and n OEU of kn. Yeah, that's reversed. But these are pieces of it that that I use certain parts of the subtle cardinal hierarchy, and how much I need of the subtle cardinal hierarchy is clear from the proof what you naturally need, but there's no reversals for that. That's from a previous thing. All right, that's 4 of them. Now there should be another 2 connected here, another 2 with here. I'm not going to do the number 2. That won't help. That's not a good idea. There's 2 more here. I just wrote 1, but there's 2 more here. One when you fix k, and the other when you fix n. And what you get is k minus 2x and n minus 2x. So this is not quite how this will appear, but it is as a corollary. All right, so that's clear. Joint usability, I haven't determined the scope of this, but I do know the basic things that I want there. That are important. That are good to do. So, and they actually, the natural statements in here are easier to reverse than the statement I do reverse. All right, and then this talks about how I actually make all this formal. And then I do graphs. Emulators is just an important thing that for gifted high school, it's an emulators is a alternative to maximal chains. But I definitely want to talk about simple graphs and how all of this is equivalent. In other words, maximal chains is basically the same as maximal cliques for our purposes. So that means that we get this statement, maximal cliques, this statement that's been reversed, this statement that's already been reversed. So anything here involving k and n, all of this stuff involving k and n, if k and n are arbitrary, then all that stuff reverses to con SRP via this. Okay. We talk about, there's a lot of further investigations. All right. So this stuff is, this is old, this is background stuff. This is maximality without embedding. Yeah, maximality without embedding is old. It's interesting because in chapter 2, which is the core math stuff, There I do embedding without maximality. The core math stuff is embedding without maximality, and the and this section, introductory section, is maximality without embedding. And then if you have embedded maximality, then of course the explosions with large cardinals start. Okay, so this is subsections of 3.3. So we have to introduce the real setting of this stuff, which is maximal change in order invariant relations. There has to be some propaganda connected with how interesting order invariant relations are and how interesting maximal change in order invariant relations are. I mean, it's a very natural idea, but there probably should be some propaganda and exercises and remarks about these concepts, order invariant relations on -1 to the k, and maximal change in thereof. That meant that what the maximal change look like is a subtle matter. All right, so then we start the real thing. Okay, so let's we did this last time, but it's been polished up some. All right, embedded maximality. So we have a partial, this means partial function in the double colons. Uh, a k-dimensional set is F embedded if and only if F is partial map that's 1, 1. As I remarked last time, it seems, according to the AI, that whenever you talk about embeddings, you demand 1, 1. Although here it turns out, and I'll make it a remark somewhere, that if you don't say 1, 1, it doesn't make any difference. You can prove 1, 1. You can prove strictly increasing is necessary, even without assuming 1, 1. Okay, so it means that for every P1 through every tuple, the tuple is an S if and only if the image of the tuple under the function is an S, if and only if, though. We say that F is an embedding. We sometimes say that S is F embedded. Oh, F embedded is the official definition. So F is an embedding. F is usable if and only if every order invariant relation on every -1, 1 to the k has an F embedded maximal chain. This is the basic concept of usability. And k usability just means that it works um, for fixed dimension k. All right. Now, what's the embedded maximality program? It's to determine the usable F. That's it. Just to determine the usable F. And this is far from understood. And by the way, also, even more elaborately, to determine the usable F and determine the set theory needed to determine each usable F. I think I want to add something like that. I mean, we care about the mathematics of this because we know that we can't determine, in some sense, we can't generally determine, certainly, in ZFC. There is this reversal, although the reversal is lacking in precision. We handle one usability. I would have to go over that again. We handle stability of usability. We don't have to go into two necessary conditions on usability. We get a hierarchy in dimension. Okay, so we have this section on finite usability, which completely determines what finite functions F are determined. Oh, by the way, we have a convention that I keep reminding the reader of. The convention in this chapter, at least, maybe the whole book. No, maybe I should say the convention in this chapter is that F is always a finite partial function on -1, 1 to -1, 1, one-dimensional. It's always a finite partial function that's non-empty. So this gets rid of some trivialities that don't have to be mentioned, that F is non-empty finite. Okay, so the finite usability theorem says the following are equivalent. F is usable, F is 2 usable. That is dimension 2. And also F is strictly increasing and certain patterns don't exist. Certain patterns don't exist involving just the endpoints. Okay, -1 and 1. All right, now there's also a corollary, finite use, star. A finite function is usable if and only if every 2-element restriction is usable, is 2 usable. So just the tiny, looking at 2-element restrictions, in other words, domain cardinality 2, just looking at 2-element restrictions and just looking at their 2 usability is enough to guarantee finite, that the whole function is usable. But this is for the finite case. Okay. And so now our subject begins here. Yeah, here I remind us of this convention again here. All right, outer extension usability. The outer extension of finite F of F extends F by the identity on all rationals that are either entirely below or entirely above the field of F. So here's an example. The outer extension of F is when you go higher than oh, this is silly here. This is silly here. When you go higher than 1/2, you're the identity. And when you're lower than -1/2, you're the identity. Okay. And this is the formal definition. Just obvious. See, because this is the part that's strictly above. This is the part that's strictly below the field. Okay, now the outer extension usability theorem is the primary theorem of the subject. If finite F is usable, then out of F is usable. If finite F is usable, then out of F is usable. And we prove this. However, the proof uses the large cardinals and we can reverse it. Okay. If finite F is usable, then out of F is usable. That's independent, equivalent to con SRP over WKL naught. All right. Now there's a weak form of this. If finite F is usable and it fixes an endpoint, then out of F is usable. And that's obviously weaker because I demand that F fix an endpoint. An endpoint is just -1 or 1 of the interval -1, 1 closed. And the nice thing about it is that weakens the statement and makes it equivalent to consistency of Erdős-Radó cardinals over maybe RCA naught. Yeah, probably I use that. All right. Now we prove it. We prove WOEU in ZC, and the proof is highly unusual in that it uses infinitely many uncountable cardinals. Now, what kind of system do you want to say is it's not provable in? Now, I have not stopped to do reversals other than the main one. So it's a conjecture that there's no proof in the system ZFC with power set removed, and instead putting in the scheme V omega plus n exists. In other words, you can iterate the power set on V omega, any number of definite times. Okay. So we just have two simple statements at the head of this subject. Um, I mean, we do. Okay. So now we're going to talk about. I limit considerably what variance I'm going to consider. All right. So on the informative side, we can calibrate OEU by the dimension and the size of the function. So OEU of Kn is if the field is n, excuse me, if the cardinality of the field is n, and f is usable, then you can use k use the dimension the out of f, the outer extension. So that's what OEU of Kn is. Obviously, it follows from OEU. It's just a way of calibrating with K and N. And also, we can do this with a weak one. We can also put in that the cardinality of the function is N, and we're trying to get dimension K usability, and that F is usable and fixes an endpoint. Yeah. It turns out that when I actually get down to actually proving these statements, it's best to tweak them a little bit in equivalent form to make sure to facilitate the proofs of the statements. So here we have OE prime of Fn, Kn. The field is an n-element subset of 0, 1 containing 0, strictly increasing. Oh, sorry. Well, hello. Um, all right. So OEU and WOEU are the lead statements of the embedded max value. The calibrated lead statements are these OEU-KN and WOEU-KN. And these things are technical variants that we actually prove. And then I have a section where I actually prove these are all the same. I mean, not these all the same. These are the same. And these are the same. The weaker one is quite a bit weaker, of course. Yeah. All right. This is no different. This is not changed. This stuff. Okay, here we have the case of one dimension and also the case of um, cardinality one function is these are trivial. This one's not completely trivial. The other one is completely trivial. This one's slightly non-trivial. You have to uh, characterize. You'll have to look at the theorem done much earlier in the book, in the chapter called characterizing one usability. Oh, here it is. Yeah, here it is. This is what it is. Yeah, we talked about that last time. And so now this is organized like this. So this is the two-dimensional case. And we actually prove OE prime of 2n because it's proved to be equivalent. And so we let the field of F be an n-element subset of 0, 1 containing 0, and F strictly increasing. And then we want to show that out of F is 2 usable using the assumption that omega 1, using the cardinal omega 1. Now, if n is equal to 1, this is all trivial. So we assume that n is at least 2. And we can normalize F using full isomorphisms. So we can assume the field is normalized this way because of isomorphism. This is an order theoretic subject, so the numbers don't make a difference as long as you respect the endpoints, which are different. Okay, and the dichotomy arises according to whether 1 is in the field or not. See, if 1 is in the field, this is the kind of thing you get. And if 1 is not in the field, you're going to stop short of 1 here. So we fix an order invariant R and assume that we're in this case. We construct an F-embedded maximal chain. In that section at the end, the cleanup section, the field is actually stopped short. And we do something. So there's a lot of commonality, but this is how we start. And we define these 3 orderings, less than star, less than double star, less than double star squared. I think we've been through this a lot. I think this has not been changed or made any neater. I think that this is pretty much. So this is the real space one looks at. And one puts 3 orderings on them. The last 2 are well orderings. This one is a well ordering on W, and this is a well ordering on W squared. Okay, this one's a dense linear ordering, and this one's a well ordering. So they're quite different. Okay, we've been through this. We lift the whole, so we lift the situation in Q, we lift it to W. See, W with less than star has the same, is a dense linear ordering with both endpoints. So is -1, 1, right? So this is the transfinite. This is the transfinite version of what we are starting with. Okay, everything's now lifted to the transfinite. Yeah, and R star is a relation on W squared because R is a relation on Q squared, on -1, 1 squared. So everything's analogous. And then we build the canonical transfinite greedy chain. We just, by transfinite recursion, we build the inductive chain, ICH. That's uniquely defined. And because it's built by transfinite recursion, we have that if we stop anywhere, we're going to have a maximal chain in the subspace that we stopped at. That's an important idea. Okay, now in all of these cases, so I guess I want to unify this, even though I say it each time. In all of these situations, we find there's a master closed unbounded set that's important. It would be closed unbounded in kappa when we do the one with large cardinals, but for omega 1, it's just closed unbounded and it's set up for a lifting lemma where you lift the largest thing. Okay, so and this closed unbounded set is done by model theory, as we've done many times. We look at W of alpha without the endpoint, but instead artificially with the endpoint minus omega 1, 0. We want to make sure that we pick the alphas so that this is an elementary substructure of the real thing, of the real thing. And that's done by filling in the gaps. The usual thing about filling in the gaps. You can do this straightforwardly. And then we do something like a Gödel collapse argument. We get that when you do this, the big structure is isomorphic to the one where you use alpha comma 0 instead of omega 1. And the isomorphism is the identity on W alpha without the alpha 0 and sends omega 1, 0 to alpha 0, just as you'd expect. Now, this gives you a lifting lemma that's very important. If let alpha be less than beta be from E, and we're lifting from alpha to beta. So we claim that alpha 0 can be replaced by beta 0, and alpha 0 can be replaced by beta 0 on either side. I guess it's also true that you can, even when you, well, let's not worry about that. That comes later. Okay, so this is a lifting thing that you can always go from alpha 0 to beta 0 as long as your parameter is smaller. And that comes from this up here. Right. Then we want to prune E. So we take care of the case when, we take care of the case where both terms are from the set. See, so we're looking at alpha 0, beta 0, and comparing it to gamma 0, delta 0. So if they're order equivalent, then you get membership is the same. And that's just that's just Ramsey's theorem. That's just a very simple application of Ramsey's theorem. Yeah. I guess Ramsey's theorem. Yeah. All right. So the finite Ramsey's theorem. Well, not the finite one, the infinite one. Okay. So then we just list the first omega elements. And then we can now when we have that, we are now prepared to lift the original function f that lived on Q. We can now lift it to f star. It's transfinite lift. I mean, it started off finite. Now it's still finite, but it's lifted. You see, using the lambda 0 through lambda n. And then, of course, we can define out. We can define out by just doing what we did in the rationals. We just do it here. We make sure it's the identity below the field and above the field. There's nothing above the field because this is a case where we're working with a case where the original function has field that contains 1. So there's nothing above for the outer extension. Okay, so then we have to verify this. This is the important thing. We have to verify that we've solved our problem in the transfinite. And then the rest of the argument is to show that if you solve the problem in the transfinite, you solve the problem in the in the original countable setting, the original setting on the rationals. Well, rationals in minus one, one. All right. So we got to show that ICH R star restricted to this part here is a embedding, is an out F star embedding, embedded rational maximal R star chain. That's what we want to check. And that's actually uh, not too hard. You just dig in and write out what the equivalences are. When it comes to this is exactly the place where when we do it needing large cardinals, we have to use some some careful large cardinal combinatorics at this spot. But here it's easy to do it by hand. Okay, so how do I get this thrown back into the rationals? Well, you take an you just form the structure. You just form the structure that we're talking about, um, and take an elementary substructure. Take an elementary substructure of the structure. Just take an element. I guess this F star gets preserved. This F star becomes the same. I think that's right. Yeah, because it's finite. So we can probably drop that because it just operates on these and these constants. So you take the elementary substructure, well, it has to satisfy the same sentences. So it satisfies that we have that ICH is an out F star embedded maximal R star chain. So it really is. So that's exactly what we want to have happen in the rationals, but we're not quite in the rationals. We're in some countable approximation to it because we're doing a column of elementary substructure. So we have to argue that this is isomorphic to some, I guess I don't need this anymore, this restriction sign, is isomorphic to something like this, where we have the real F over here, the real F, and we have the real less than um, instead of this fake one. And we have some set S. Okay. So the set S is going to be the embedded maximal chain, the outer F, outer extension of F embedded maximal chain in R. It's going to be the one we want. All right, now these other, so this takes care of the case where we've used up all of the interval. In other words, one is in the field. And then if we want to handle this, we have to modify this. What we do here is we just tack on some non-transfinite silly part, Detz's part on the top, you see. And our eventual out stuff will use this, you see. And there's really no difference in the proof. So I'm going to try to figure out how to I consolidate these things without repeating much. That's an expositional issue. Um, so this is the obvious ordering less than star. This first, this second, this is just a point, and this third with the usual ordering. But then the other orderings we need are well orderings. And so for that, what we do for that is we actually put this, for the well ordering, we put this in front here. We actually put this in front before we do this. You see, that's an interesting idea that the well ordering is different in that way. So we put 1, 2 up front. And actually, when we put it up front, we might as well, we start with 2. I mean, we got to start, it doesn't make much difference how we do that, but as long as it's up front here and well ordered. Okay, so, and then everything goes through just like before. We will get the transfinite um, the transfinite out F star embedding. The transfinite out star embedding will work because those inert things that are put in the front with the transfinite recursion are innocent. They don't really change anything. So we get this. So we get the whole thing, the whole shebang here. We get OEU of 2n using omega 1. Now we want to fix n. I guess I will barely finish this, but let's quickly go to this because we want to do the one with the large cardinals. We want to say something about that. So here, the function f, the field is a 2-element subset of 0, 1 containing 0. So it's just 0 and 1 or 0 and something in between, which we normalize to be a half. And so we have 2 cases like that, with the main case being when it's 0 and 1. And it's a strictly increasing function. So it's either the identity or it's just a function that's defined at 1 only. Yeah, and it's defined defined at 1 only or 2 only. And it's the other number. So sorry, 0 and 1 is what I'm talking about. So it's f of 0 is 1 or f of 1 is 0. Okay. Okay, so we actually make the construction exactly the same, except that when we get to the lambdas, which we build the same way we did before, exactly the same. When we get to these lambdas, well, okay, here's when we got to the lambdas. We're just going to use the first 2 of them. We're just going to use lambda 0 and lambda 1. That's all we're going to use. We don't even care about the others. And we get this major thing just by brute force, by just looking at what you have in front of you. You can compute that. And then we do the isomorphism back. We put it into the rationals, and what happens is that lambda 0 becomes 0, and lambda 1 becomes 1. When we do that, see, here's it with 0.5. All right, now I just want to talk about how you do this. Now you have to plug in the large cardinals instead of doing those simple things by hand. In the 2 cases involving just omega 1, here it's of course more involved. You have to use a subtle cardinal hierarchy. Okay, so I think we've been through this stuff, but I don't have time to do it today. But we can be more careful next time about how this works. But we do the same construction. Whoops, this is not done right there. Okay. Same construction. Lifted to the transfinite all our ingredients on Q. Now, we build the same inductive chain just as before. And then we build the same set E that's closed unbounded that supports lifting just the max. That's also have to be consolidated when I finally clean up the exposition. And then we need this combinatorial lemma that we can find an infinite set such that the following holds. If U and V, given alpha, given any ordinal alpha, if U and V are, they got stuff below alpha, whose second coordinates are not necessarily zero, together with all the stuff from alpha on upwards cross zero. It has to be in there. Intersect V. In other words, then and their order equivalent, and they have the same coordinates below alpha in the same positions, and there's at least one such position, then you can get that U and V are equivalently in ICH of R star. This is the key combinatorial thing you need. Now we want to eliminate this condition that there's some such position because we're going to use this to prove embedded, transfinite embeddability. And so that's done by pruning. That's simply done by pruning using the infinite Ramsey theorem. Okay. And then we have to actually roll up our sleeves and actually show that the large cardinal common torus is good enough to actually show that we have an embedding, that out of F star is in fact an embedding. What R star maximal chain are we talking about? ICH of R star, of course, the canonical one built by greedy transfinite recursion. All right, then I won't do this today because it's run out of time. But then there's the other case where we don't have one in the field, and so we have to lambda is n zero, and then we have to have some. Oh, I'm sorry. I'm still in. I'm sorry. I'm just finishing up the thing that I was doing. But what I was going to say is this section here where we actually the one is not in the field, and so we normalize it by just going up to here. Sorry, we normalize it by just going up to here, and that's handled in the case as I did before by putting this little innocent neutral copy of the rationals from, just from the interval from 1 to 2, left open, right closed, as I did before. All right, so I think that, yeah, so I'm getting close to I'm going to perfect the exposition of this, clean up the one also for, that uses the Erdős-Radó. This is all recycling and smoothing out things that happened before. There's nothing really new here. except the neatness, the powerful neatness is very important that we have. And so I should be able to wrap that up. Plus the joint, for joint usability, it's not, I'm not going to go into in great detail, but there's a clear couple of statements in there that are really worth talking about. And basically very little else. I got to say something about graphs and emulations and the reversal, but the reversal is simply observing quite easily that the key statements, the lead statements here, or the lead statement, that the strong lead statement, OEU actually implies the statement that was reversed involving maximal cliques. That's what will happen next time. And then maybe we'll get off this and be able to talk about other parts of the book, like the finite stuff, explicitly finite stuff. All of this is implicitly finite, the explicitly finite stuff. All right, so I'm done now, Andreas.